Welcome everyone. Thank you very much for joining us here today. You are in the right place if you are here for 9.Connect's monthly webinar entitled Enough with the High-Speed Theory Already, Give Me Something Real, Part 2. So in our first series, we focused on loss tangent and permittivity, which do play a major role in high-speed design. And in this webinar, we will look at what we all really came here to want to see, right? And that is to how do we apply the traces, or how do we apply this all to the traces. So I just wanted to let you know that our presentation today is going to run just shy of 1 hour. However, given the importance of this topic, we will definitely be holding the Q&A, which will run past the hour. So we hope you'll stay on the line with us for that. If you have any questions during the webinar, please do write those down in the panel. And we will look at those at the end. And we do ask that you be very specific about those questions so that Sean can answer those straight up. And just by the way, to keep you on your toes, we have a number of polling questions that will be asked through the session. So make sure that you've got your eyes and attention on this. And so with that, I'm going to turn our webinar over to our presenter, Sean Kelly.
Well, thank you everyone for being here and joining me today. Before we get started on the actual material, we are going to put up a polling question because I'd like to know a little bit more about what you all want in the future. So polling question 1, would you please just let us know what you'd like to see in the future? Very good. Thank you all very much for that. Looks like 31% general routing, that was the majority. 28% came into routing inside the PCB. That's the second most important one. And then reference planes. Interesting. Got 19%. Okay. So the purpose of this webinar series is to help give you all practical understanding and solutions relative to high-speed designs. The last webinar we had discussed relative permittivity, as Paul was talking about, and the loss tangent. Now, if you hadn't attended that webinar and you would like to watch it, just please contact us. Part 2, which is going to be today, and we're going to talk about PCB routing concepts and issues that you will see, especially if you're starting to look at other people's designs. You'll be able to spot what they're not doing correctly. Now the next webinar, which will be part 3, we're going to talk about problems, material selection, and stack-up options. That's going to be a very interesting webinar, and I would definitely want you to come back for that one. So polling question number 2. Kind of get an idea of how much you already understand about relative permittivity. Okay, so it looks like we got 2 pretty definite majorities, with 40% said C and 36% said E. Actually, E is the correct answer. It's going to decrease the speed greatly. If you've never looked into this kind of concept, I think you're in for a real surprise at just how dramatically the permittivity affects the speed of a wave. We're going to talk about 2 specific equations and terms. The first one is a velocity factor. It defines the relative speed in which a wave moves through a medium. The relative permittivity is going to influence that wave propagation. Now, if you'll notice, I put a little asterisk here to define that the velocity factor being 1 over the square root of epsilon r, so you see that it's inversely proportional. This is an equation that has been around for a very long time, and so we're not going to derive it. It's just accepted as a standard equation and accepted as fact. But also created this table over here on the right so that you can see that, generally speaking, with a lot of the PCB materials that we use for have as dielectrics, those general numbers and then how the velocity factor relates to it. In an ideal dielectric, we would have that velocity factor equaling 1, and therefore the wave would move at c, which is the speed of light. You'll notice down here, what I've done is shown you that if the relative permittivity is 1, which air is, then the velocity factor is it travels 100% the speed of light. And you calculate that out, it's approximately 11.8 inches per nanosecond. Now the velocity of propagation actually defines the velocity in which a wave moves through a medium. Again, the equation is, we're not going to derive it. it's accepted as fact, is the velocity factor times c, or c divided by the square root of epsilon r. So the one thing I want you to notice that we're going to show more and more is, especially FR4 type materials, you'll see in the range of 4 to 4.4 that the speed in which the wave is moving is less than half the speed of light. Also notice that this velocity is inversely proportional to the epsilon r. So again, as the dielectric constant goes up, the speed decreases. Now, you'll hear me using the term velocity and speed interchangeably. I know technically velocity has direction, but in this situation, we're not worried about the direction per se. Most of these signals are bidirectional, so that's why I use them interchangeably. Again, if in an ideal situation, we would want the dielectric material to have a velocity factor of 1, and therefore the wave would move at c. Now we're going to round off 11.8 as the speed of light, but technically speaking, that's what it is. And again, as the relative permittivity increases above 1, it slows the wave, and therefore the signal is delayed proportionally to the velocity factor. Again, if epsilon r is 4, which is very common, the velocity factor is 0.5. It means it takes twice as long for a signal to propagate through a medium. When you start to understand this delay factor, then you start to realize that length tuning is more than just the physical length. You've got to tune it electrically. Some examples: single-ended type signals, clocks, and data. Differential signals, you have to worry about that tuning within the route pair itself because they're relational. And I'm going to talk about 3 specific cases. In this first case is just a transmission line separated by air. Because air we know has an epsilon r equal 1, then everything travels at the speed of light. That is 8.8 or 11.8 inches per nanosecond. Therefore, it takes about 84.75 picoseconds to traverse 1 inch worth of material. In case number 2, stripline, where you have a trace that's actually down inside a PCB, if we use FR4, for example, and have epsilon r equaling 4, the speed being half, then it's also half the speed of light. Now, interesting enough that the delay incurred is irrespective of t, that is the trace height, the thickness of the copper, and the width of the trace, or the plane-to-plane distance, in other words, how thick the substrate is. The only thing that matters is what epsilon r is for this dielectric material. Therefore, you'll see that it calculates out to 169.5 picoseconds per inch. So polling question number 3. All right, so we said 33% of you all said true and 67% said false. Congratulations to the majority. You got that right. So again, the speed is going to be inversely proportional to the dielectric constant. So if I decrease the dielectric constant, then I'm going to be increasing the speed. Now, third case, one that probably a majority of you all are very familiar with, is a microstrip. It is a much more complicated situation because the fields are going to be traveling through 2 different mediums. That is, the substrate itself and the air above it. The velocity factor is not as simple as 1 over the square root of epsilon r as it was for the stripline. Here you have to consider more of an effective permittivity. Think of it as kind of like an average. The velocity of the wave is going to be faster than the stripline, but slower than if it were in air. And it's kind of intuitive if you think about it, because in the stripline, because these fields up here were inside the substrate, they were going to be moving slower. But if half of them fields are traveling faster than they would be in the substrate, then the average is going to be faster. So the velocity factor is actually 1 over the square root of an effective epsilon. But the problem here is calculating that effective permittivity is complicated. So why is there such variation of how fast this wave can propagate? Consider the implication if the substrate thickness decreases, as you show here, and I'll just be the first to tell you, I'm not an artist, so please forgive my artistic nature here. But what I'm trying to show you is that if I decrease the thickness of the substrate, I'm getting more of the electric field actually embedded within the substrate. What if the trace width increases? Same scenario. You still get more of the wave traveling within the dielectric. In either case, the wave propagates slower. Again, why? In each one of those two scenarios, the fields concentrate more into the higher dielectric constant material, and therefore the effective permittivity increases. Because the speed is inversely proportional to the dielectric constant, that's why it slows down. So I got another polling question for you, because most of you all are familiar with solder mask. I want to know, what do you think would happen if you added solder mask? What would that do to Microstrip's velocity of propagation? Oh, great. Oh, this is very rewarding. So 80% of you all said D, slows it down. Excellent. Okay, so what's the deal with the effective permittivity? So what I'm going to try and help you all to understand is, why is there so much confusion and why is this so difficult? This first example is with a guy named Waddell, who's created a transmission line handbook that is used throughout our field. It's very well known. And he has equations on how to calculate a microstrip's effective permittivity. So in this example, I picked a thickness of copper 1.4 mils, which is typical for 1 ounce. Trace width of 5 on a substrate that's only 3.3 mils high. If you use his equation, you come up with an effective permittivity of 3.2025. But if you use an IPC standard, 2141A, they have their own equation. It's very similar, and they come up with the same number. But if you use Hall and McCall, which is a very popular book on this type of subject, they have a totally different formula. And when you do that, it comes up with 2.9663. So if you're just trying to understand a basic microstrip, you can go through and create a spreadsheet like I did here and show all the different equations, and you can run through the numbers and see, in this case, what the variations are for the different equations. Now keep in mind, the equations have two conditions. It's based on the ratio of the width to the height. So what I did in my spreadsheet here is I just put the conditional formatting, and since I'm in condition greater than 1, then this right-hand column is what's valid. So you can see that with Waddell's equation, Hartley's equation, the IPC standard, Hall and McCall, the variation that we get. And then if you use some common online calculators like TXLine, Saturn, and AppCAD, what they show as the effective permittivity. So there's quite a variation in there. So the question is, how does that impact me as far as based on which one I use? Now, before we get into answering that, this is great for one microstrip, but most of us out there that are doing circuit boards, we have multiple layer circuit boards, 6, 7, 8, 20 layers sometimes. And so this would be a very tedious process to do this with a spreadsheet. So I like to use a program called ICD Stackup Planner. And when I go ahead and create my Stackup, it has a built-in tool that allows me to automatically find out the flight of time, or time of flight, for all these traces, no matter what layer they're on. So it saves me a ton of time. So what I want to show you is how I can use this tool compared to Excel. So I set up for a 1-inch path. And so if you'll notice that in my equations in my spreadsheet, so what I came up with is on a strip line, this time 175.6901, and ICD Tool Planner came up with 175.17. That gives me a difference of 0.5201 picoseconds. Not a whole lot of difference, so that reassures me that this program does its job. Now if you notice, the microstrip, the flight time is much lower. Again, remember we said that the effective permittivity is lower on a microstrip, and because it's lower, the time is faster. So what's nice is this also shows you a bar graph of the relative speeds of these different traces. And it's got a little button down here, and I can just say I want to match the delay. And if I do that, it will automatically show me that 25 picosecond microstrip being faster can be tuned out. So it'll electrically tune based upon speed, and it shows me that they're tuned. And now you can see that the flight time of the microstrip is the same as a strip line. Notice how it made the microstrip longer to 1.1724 inches. So it automatically lengthened the microstrip so that the wave would end up at the end of the 1 inch simultaneously as if it were in the strip line. Now, the one thing about the tool is it doesn't give you the effective permittivity, but not that you really need it. But for an exercise, you can work backwards with the equation and calculate it, since we know what the velocity of propagation is from the tool. When we did that, I found out that it's 3.1098, which is in the middle of the range there between the different equations and the tools that we used in the spreadsheet that I showed earlier. So the ICD planner comes in between Waddell's equations and Hall and McCall. Now, interesting enough, neither Waddell or Hall and McCall include the solder mask. Now, if you remember back, if I go back here a couple slides, you'll notice this does show the solder mask, and it assigns it a dielectric constant of 3.3, which is very typical. So the ICD planner, Stackup planner, does include that. So polling question number 5. Yeah, so 29% show nothing, 6% show 3D solver, 7 a Stackup planner, 13 for a spreadsheet calculator, and 44% use online tools. Interesting. So let's relate the tolerance that we showed earlier from the different tools and its practical application. So if we look at the swing between the lowest number and the highest number, at 2.9557, that delay relates to 145 picoseconds. And at the 3.2025, the delay is 151 picoseconds. That difference is 5.9594 picoseconds, which at the rate of 6.6 basically mils per picoseconds, that means there's a 39.3 mil length variation in that propagation. So if you have a trace that's 10 inches long, you could be off as much as 393 mils, depending upon which one of these numbers you picked. In the real world, what that translates to is 59.59 picosecond possible skew. That is a period of a 16.8 gigahertz signal. Now, you might think, if you hadn't watched the previous webinar, wow, that's really high frequency, what do I care about? But if you remember, we talked about some of the higher data rates of 10 gigabits per second. We had to be worried about 25 gigahertz signals, or 25 gigahertz frequencies. So this is definitely in the realm of being a major impact on your design. But remember, the goal is not to be perfect, but to minimize the probability of failure. So when it comes to signal speed and propagation delay time, we're going to talk about some conclusions and some design considerations. The traces on the outside of the PCB travel faster than those that are embedded. This is important here. Thinner microstrip facilitates faster propagation but the PCB supplier ability to maintain the characteristic impedance tolerance is going to be varying with that characteristic impedance design. The narrower the trace, the more difficult, especially if it's lower than 7 mils, to maintain that characteristic impedance. To calculate the speed, one needs to use effective permittivity, because a microstrip has at least 2, and 3 if you consider the solder mask, different epsilon R to deal with. Stripline has 1, assuming the conductor is sandwiched between the same material. The effective permittivity equations give quite a range, and they don't include the solder mask. The only true way to know is to create the PCB and then test it. So if you're in a really critical situation, take the few extra days and a couple dollars, build a piece of a board out of the material, just some straight traces, and just measure the time that it takes, especially if you already know which board house you're going to be going with. Now, as far as the solder mask itself, if you add that into the picture of a microstrip, that's called an embedded microstrip. When that solder mask is involved, what else shows that calculating the buried effective permittivity is conditional on knowing the effective permittivity of the microstrip? Well, as we've demonstrated already, we have quite a bit of ambiguity and uncertainty in those numbers. So in our example, when we used Waddell's equation, we came up with a microstrip effective permittivity of 3.2. His equation shows that the new effective permittivity that's buried is 3.26, which is higher. Going back to what we talked about earlier, that the more you force the field to propagate through a higher dielectric material, the slower it's going to go. And if you add higher dielectric material on top of the substrate, then you are increasing the average, so to speak, amount of material that the wave is having to propagate through. So this makes sense. So polling question number 6. Since the effective permittivity of the embedded microstrip increased, what is the net effect? Wow. All right, we got 90%. Getting close. Yep, 89% got the right answer. The wave is going to travel slower. So just be aware that if you pick a solder mask, it is going to affect your tuning, and if you tune your length correctly. Now, we're going to talk about how people lengthen the microstrip to create this tuning. So one of the more popular ways is called serpentine traces, sometimes referred to it as meander lines. So I've shown you a picture here is if I've got a source of a signal and it's got to arrive at 2 different loads at the same time, well, because the strip line is slower, it just traverses through straight routes. Since the microstrip is traveling on the outside of the board, it has to have a physical delay line built into it, and that way the wave shows up at the same time at the load. Now, there's 2 different serpentine types, and it's going to be based upon single-ended or differential signals. For a single-ended, you typically think about either close coupling or loose coupling. In close coupling, you're going to use a rule that says that the serpentine has 3 times the height of the dielectric. So if you're on a 10 mil dielectric, then you want at least 30 mils between the long parts of the serpentine. For loose coupling, it's going to be 5 times that spacing. With the 5x rule, it's going to be slower, less crosstalk, and less noise. And the delay is going to be very close matched to a straight route. So why don't you want to use it? Well, obviously, it's going to take up more room. With a 3x rule, it's faster, less area, but the complication is it has more crosstalk. Now, for the reason why it's faster is if I've got a wave that's trying to propagate through this material, it can already see that this is where it's got to go, and so it's going to kind of bleed over to it. It's like trying to take a corner in your car. You want to cut the corner real sharp. That's kind of the way the field is going to behave. So it actually moves faster. Some rules though, you want to minimize the length of the serpentine sections as much as possible. This is going to reduce the total magnitude of the coupling. In other words, what I'm saying is this length here directly influences the amount of coupling and creating crosstalk. If significant lengthening is needed, consider a spiral inductor. There's a neat article written by Barry Olney, and he has shown that one way to deal with this long serpentine is to create a spiral inductor. Whatever you do, don't serpentine clock traces. If you do, make sure you have definitely a 5x rule, if not more. Now, differential length matching. Differential matching is much easier because the traces are routed together as a pair. So the general thing is, I want you to keep in mind, is with the differential pair, you want to try to maintain the differential impedance. So if you've got an Ethernet at 100 ohms or USB at 90 ohms, you don't want to cause this section of your trace to go too far away from your main trunk here, or else you'll go away from that differential impedance. So what they tell you is don't extend this portion of your length to more than twice the spacing. Matching should be done per layer for the length on that layer if at all possible. And so in other words, if you're meandering through a board and you have to go from the microstrip down into, let's say, layer 3 to route in Stripline for a while, and then you have to drop down to layer 15, then you got to come back up to layer 1. You want to do whatever tuning of matching the length within that layer, if at all possible. If we look at the signal traveling from left to right, delay the appropriate signal as close to the source as possible. So think about it this way, and this is what I tried to drive home in a prior webinar called 50 ohm, what is a 50 ohm characteristic impedance? You got to think about this as a wave propagating between these two conductors. Well, that means that this wave, where the charge is maybe, let's say, positive, and this is a negative charge, it's going to want to look as a wave from here to here. But at the same time, this wave has got to move through this particular line. Well, this one's moving up this way at the same time. So you were trying to get this one to slow down so that this one can catch up. And then from this point forward, the wave is traveling on a symmetrical type of homogeneous way of looking at the medium. And then, of course, this is a symmetrical breakout going through to the other part of the board. So what's wrong with this picture here? This is a USB example that I was looking at from a client. The positive signal is going to travel on the top longer than the negative signal. And there's no vias for the reference plane. So if you think about the wave leaving this IC, getting on the board, getting on the traces, it's moving nice and parallel to each other, and then all of a sudden you've got part of the charges or the wave going down into the board. At the same time, you have part of the wave still sitting on top of the board. So it's almost like it's having to go diagonally through the board material. That's not good. The consequence is the wave is not propagating with the symmetrical wavefront. Another way that you could do this, I would say, is a better way of transposing the relationship, and this happens a lot where the USB lines, they change polarity and you don't have the ability to swap them on the IC, is you can change the direction when moving from layer to layer. So if, let's say, this is the positive and you need it to be over here, then you just come up here and then you back to, you go to the other side, and therefore it is now on the different side going to the load. Notice also you have ground vias sitting here that help tie the two reference planes together. And we're going to talk a lot more about reference planes in just a few minutes. One thing that I've noticed over the last, 10 years or so when talking to people about differential impedances is they seem to get or not contemplate or keep in the front of their mind the need to monitor the common mode impedance. So if you look at the spec on, let's say, USB lines, and they say 90 ohms differential, it also includes a common mode impedance or a single-ended impedance. That's because there are still going to be fields created in this even mode of transmission. If you get back to why we are doing differential signals to begin with, it's one of the things is to keep noise levels down. Well, how does it do it? Is it tries to make sure that any signal that's being induced on this trace and this trace are symmetrical. Well, if these impedances are not kept symmetrical, then that common mode noise gets converted into a differential noise, and that's detrimental. Now, here's an example of somebody that routed a board for one of the clients, and he started off really well, but noticed that he the matching of the length was put together here. And this is the USB 3 line, so they're bidirectional. Since they're bidirectional, let's spread the wealth, that is the correction. Place an equal part of the length matching as close to possible as to each end. So if I put part of the length matching up here and part of it over here, then I've got all this length here that doesn't have a huge amount of deformity in the wavefront. Now, Barry also created another article called Skewed Again. And this is a thought process that I thought was definitely germane to our conversation here. And want you to think about this situation. So in his article, he talks about keeping corners at an equal count. Again, the concept is matching length. It seems simple, but it actually is quite a common error. So on this polling question, I'm going to leave this up for a few minutes, and I want you to look at this image and tell me, which pair do you think is the problem? Write down your answer, and then we're going to take this image off and actually put the polling question up for you to enter your answer. Okay, that is awesome. So 55% got the right answer. The answer is D. And here's what I want you to understand. So in the pair A, you see that you have a short and a long and a long. So this outside trace is going to have a longer period in which it's got to try to traverse this. So we should technically create some kind of delay line on this inside trace. A lot of people, when they first look at this, say, oh, it's got to be pair B. But actually, pair B is exactly the way it should be done, because we are creating an even number of shorts and longs on every trace. So this short is compensated for by this long is compensated for by this short, and this short is compensated for by this long. So it's almost as if there were never any bends in this entire path. Then you look at pair C, you'll notice that this length or long and this short is compensated for by this long and this short. So they balance out, they negate each other. So the net effect is you have exactly the same situation as you do in pair A. Microstrip versus differential, or I should say single-ended versus differential. Why use differential signaling anyhow? If you don't know why, then why would you know what is good or bad about your routing techniques? So the goal of doing differential traces is to increase noise immunity from external sources, decrease the sensitivity crosstalk from other signal lines, and it's going to effectively double your slew rate and improves your signal-to-noise ratio. So when you're routing a differential line, these are the things that you're going to try and keep in mind of, does your route help meet these goals, or is it going to be detrimental to meeting these goals? Let's go over a few general routing rules. Pad exits. The goal is to reestablish the differential impedance as soon as possible. So in this situation, if you had a BGA part, notice that in the best situation, we have symmetry in the routing, and we can, as soon as possible, recreate the proper separation of the traces in order to create the differential characteristic impedance. In this scenario here, it's okay because we have done the matching of the length, but again, this is not the ideal situation because you have a greater separation, therefore the characteristic impedance is not right on target. These two situations, they're fair, and they'll probably work on some of the slower differential, but if you start getting into the real high gigabits, this is not going to work very well at all. Lumped components. A lot of times there are DC blocking caps put into place on a differential pair, and so you have to deal with that. Again, the goal is to maintain the differential impedance as much as possible. So in this first scenario, you want to keep the trace at the right spacing for as long as possible until you get to the lumped component, and then as the signal propagates through, you're trying to reestablish that differential impedance. There are a couple good articles, by the way, if you want to do some more research on how to deal with trying to make this single-ended impedance here match this single-ended impedance. That's a long discussion. But the last thing you want to do is separate the components like this so there's no symmetry, because now you've got a wave that's coming through here in a uniform, symmetrical manner, and all of a sudden it sees an impedance on one line that's not the same as the impedance on this part of the wave. And then it's got to change because this impedance is different. And then it comes back together. So that's a big no-no. Anti-pads. Now, as we talked before, the differential impedance line, you also have a single-ended impedance portion of that proper routing. So in an anti-pad, when people create vias, they'll relieve the copper pore around it so that they don't have parasitic capacitances. Well, if you route a differential line over an area where that copper pore has been relieved, then what you've done is you've influenced the reference plane underneath it. Well, if you don't maintain the reference plane, then you're changing that single-ended impedance. If you change single-ended impedance, then what you're doing is giving more ability for common mode noise to be converted to the differential noise. Pad entrance and exit. Now the right side, if you'll notice, has an abrupt impedance change. The track comes in, goes right here. These sharp edges do create reflections. So the left side is a much smoother transition and tries to maintain that differential spacing longer. So that's the ideal way to do that. Again, reference plane clearance. If you have a void in a reference plane, you want to maintain a specific distance away from your differential lines. Remember the rule that we talked about earlier about the 3H and 5H? Well, general rule is at a minimum, you want to keep 3 times that separation of the dielectric height away from any voids in your reference plane. Maintaining the reference. You can add vias and tie the reference planes together. This helps keep the common mode impedances balanced, sometimes referred to as stitching vias. Now let's talk about reference planes. You really need to get out of the habit of saying ground plane. A wave composed of electric and magnetic fields travel because of an EMF, that is an electromotive force, that is applied to conductors. EMF doesn't care about a ground, it only cares about the positive and negative terminal. For example, you could have a floating system, there really isn't a ground, but the EMF is applied to positive and negative terminals. A reference plane considered any DC level. You might remember this picture below from one of the other webinars we did on what is a 50 ohm characteristic impedance. And I was trying to explain to you that when you apply this voltage, that the charges that are moving create a differential voltage, and that differential voltage propagates down this line. You would be better served not to think of current, but instead just think about the moving voltage because of that current. Here's what I mean. If you picture the wave moving away from the EMF source and consisting of an electric field between those two conductors based on the difference of potential, then it doesn't really matter if you see the below circuit as single-ended or differential. Anything that impedes the wave from forming between these two conductors in a uniform and consistent manner is going to be detrimental to the concept of your signal integrity. With that in mind, I want you to look at the shape of the fields in this picture below. Notice they're fairly uniform in shape between the two conductors. That is, this top microstrip and the reference plane underneath it. If you were to watch the wave propagate from front to back, in other words, from this side to the end over here, it would maintain the same shape because the geometry is symmetrical and uniform. Anything that changes that symmetry, uniformity, is going to change the wave shape. That is going to be detrimental. Technical notes, app notes, technical books, they like to talk about return current and loop areas. While technically correct, those concepts go back to the fundamentals of electrical engineering. But to me, it is easier for the concept to be intuitive if you think of the wave as a difference in potential. I know technically it's the same thing ultimately, but if you see the charges moving in lockstep. That is, the positive and negative are moving in the same direction at the same speed, and they're trying to see each other in the same relative position, then it's easier to understand when you're routing something incorrectly. In the 4 situations that you see here, for example, they're saying the source can start here, go on a top layer, come through to the bottom layer, and come back. That's one way. And this would be definitely a DC path. For us in the high-speed realm, this is what we want all the time. So let's assume that the arrows on the red arrows represent the current on the top layer. The blue arrows represent current on the bottom layer. As you can see on the right, A, B, and C all would follow Kirchhoff's current law and work just fine at DC. However, in high-speed design, only B would work. C and D are major problems. A is never going to happen as shown when we're talking about high-speed situations. So what we've done here is, in high-speed digital design by Johnson and Graham, he does a good job of explaining this. So we have a picture here where we have a source, and the way the charges are moving through the top, through a wire, go through a load, and then they come back through the reference plane. And notice they pick whichever path they want to come back based upon least resistance. Return currents behave differently based upon the frequency of operation. The higher the frequency, the closer the return current will be to the other conductor. So as Johnson and Graham point out, that as you get higher and higher in frequencies, the more and more the path when on the return is going to follow the same path as it goes out. And it treats it as if it's worried about the least inductance, not the least resistance. Here's a nice little thing that shows you here that the distributed current or charges is going to be based upon where the microstrip is. Because return currents behave differently based upon the frequency of operation, then those return currents can use coupling capacitors to jump from a ground plane to a voltage plane and then back again. You can use a capacitor to jump over voids. Here's an example. You've got a microstrip that's trying to move from one point to another, and when it's trying to come back, the return current, it's got to jump over this void here to go from one plane to the next. So you can use a stitching capacitor, and it was going to tie those two reference planes together. So technically speaking, yes, the return current is here, but if you look at it as if I've got a charge on the top and a charge on the bottom, and they're trying to propagate at the same time along this path, then all of a sudden they get to this break. Well, the charges on the bottom are like, oh, where am I supposed to go? They're going to try and go around here and ultimately try to catch up. And if this ground plane or this reference plane were somehow tied to this reference plane over here, then that charge would come back over this way. It really totally destroys your characteristic impedance. So I came across this as I was doing a little research, and I thought you might find this interesting. So one of the ways that people delay things is using what's called a switchback. So what they found out is, here's the zero reference in phase, and they ran a signal through a matched 33 millimeter delay, basically. Switchback is here, and here's a serpentine. And then they noticed, oh, there's a 12 picosecond skew when the signal gets out here. And so they were actually having a contest saying, okay, can anybody explain to me why, even though these are electrically the same length, they are not giving me the same amount of delay? And what they found is that they had to shorten the switchback in order to get the 0 picosecond skew. Well, again, if you look at it from the perspective of, here I am, I'm a surfer sitting on a wave on my surfboard, and I'm trying to sit on this wave moving from left to right. And if I'm traveling on that wave, and all of a sudden I get to this point, well, my wave is trying to disperse between this side going this way, and then part of my wave is going this way. And so it's stretching out. When it's stretching out, it's going through different materials. And so therefore the whole speed changes. If you think about you're sitting on that surfboard and you're sitting on that wave, then even though the wave may disperse a little bit left and right here, and it comes back together, it's still staying uniform. And it just keeps on kind of bouncing back and forth in width, but it's still staying uniform in from left to right. And so that's why it matches. Now, to relate all this to a condensed practical understanding, many online downloaded calculators are good, but they give inconsistent values. They're good starting points and work really well for lower frequency solutions. But as you move up in higher frequencies, you really need to either get a Stackup planner that includes field solvers or use a 3D field solver yourself. A lot of the problems that you're going to run into in high-speed design can be avoided using some common sense rules. Avoid impedance changes. Symmetry is important. Be aware of your surroundings as you route. And keep the wavefront uniform. High-speed designs, ultimately, your best bet is to use a 3D solver, because that can then accurately assess any out-of-the-ordinary routing issues. So polling question number 8, I'd like a little feedback from you all, if you all don't mind, is how would you rate the materials presentation today? Okay, 88% said relevant to what I need. That just makes my day. I appreciate that. And that's what I'm going to strive for in the future. Make sure that I try to get you all what you need. Part 3, which is going to be, if the schedule serves me right, it's going to be in 2 months. We're going to talk about PCB material issues themselves. And we're going to talk about problems with glass weave. If you're not familiar with that, you might want to kind of read up on it so that the discussion will make a lot of sense to you. But that's quite a complex discussion, and unless you're familiar with it, you won't have a clue as to how dramatic it can be to your differential lines in high-speed design. Then we're going to talk about mixing up materials and stack-ups. If you have a really complex situation, you can actually use different board materials in the Stackup, but you've got to be careful when you're mixing and matching the materials, and we're going to talk about why. And then we're going to talk about some typical Stackups. Polling question number 9, just out of curiosity, if you don't mind telling me how likely you are to be at the next webinar. All right, well, thank you very much for that. 74 said very likely. 24. Oh, good. Okay. So with that, I will hand it right back over to Paul.
All right. Thank you very much, Sean, for that wonderful webinar. Anyways, again, thank you very much for your time, and we look forward to having you next month. Have a great day.
Folks, I'm not sure why you showed up today, but we here at 9.Connects know that topics of this nature are important to you. We know they're important for designing the PCB, especially as speeds are increasing, signal integrity issues are becoming more and more prevalent, and the demand for wireless is growing bigger and bigger each day. At 9.Connects, this is the knowledge that we sell, and we sell it in different ways. Most of you know that we sell this knowledge in the form of trainings and coachings, especially with Altium Designer, and most recently with our new PCB Fundamentals class. We're also happy to announce that we have just released 2 one-day classes for Altium Designer libraries and schematics. In addition to coaching and training, we consult, and this word is really abused because anyone can call themselves consultants. So what do we mean by it? It means that if you have any challenges or issues with your PCB design, we can assist you. You have a board that will be handling large amounts of power? We can assist. Have boards that need compliance testing or designed to be compliant to a standard? We can assist. In short, we can assist you in achieving your design. And by the way, we're more than happy to assist in board layout as well. When I was doing design, we had challenges which we call technological hurdles, and I'm sure you deal with them all the time. And in some cases, you may be avoiding features like wireless or gigahertz speed devices because this stuff may seem like major technological hurdles to overcome. But you don't have to wing it or go at it alone or even avoid it. Let us here at 9.Connects get you over those technological hurdles. So for more information, contact us and check us out on the web at 9.connects.com. Thank you very much for taking a look at this video, and you have a wonderful day.